Thank you very much. Hello, everyone. Greetings from Brazil. I am Davi Souza. Today, I will be talking about space greenhouse, specifically how would be the operation of a space greenhouse, a Martian greenhouse in the Martian habitat. I am an electrical engineering student and also a researcher at Habitat Marte Space Analysis Station. My research topic is related to greenhouses and also technological applications for space greenhouses. This is a presentation for the virtual space analog mission number 89. Well, some topics that I will be discussing here. This is the crew, and I will be covering some features on design, technologies, resources, management, protocols, and also the sustainable development goals. It's a big pleasure for me to be here with you all and sharing some of my knowledge with you. Starting with some initial considerations, this is how my presentation will be based on. This pyramid shows us the minimal features that will be necessary to build a habitat for survival on another planet. And as you can see, the base of this pyramid, the bottom of this pyramid is formed by the energetic systems and also the industrial systems. Integrated with that, we have the building. And all of this together, we can build an ecosystem. This ecosystem will be composed by the atmosphere, the ground, the water, and the living organisms. But in the top of this pyramid, as you can see, we have the human factors. So all of the things that I'll be covering in this presentation today will be considering not only the systems, not only the technologies, not only the machines, but mainly the human factors, because we will be still dealing with humans, and with that, it's necessary to consider this approach, this specific approach to build a habitat, to build a greenhouse with the human factors in top of our discussion. About the habitat, I believe the crew are already aware about the master plan that we have, the proposal. This design was proposed by Yash Hatod in mission 47. And as you can see in the left picture, the greenhouse is located in a strategic position because it's near of all the facilities. So as you can see, we have the greenhouse near of main station, the health facility, the engineering, and the sanitation center. This is really interesting because the greenhouse will be producing all of the food for the whole habitat. So considering that we already have some astronauts, some crew members in the other facilities, will be very interesting to make easier the logistic approach to deliver food for the other facilities, and also for possible collaboration. And about the collaboration, I will be talking better during the presentation. And in the right picture, just another visual concept and to show you the location of the greenhouse facility. Well, considering the internal design, I am proposing here an integration of our circumference shape with 80 meters of diameters and 2 floors, and an hexagonal model. This hexagonal model will be composed by this proposal called Mass Boreal Greenhouse, which have an 8 meters diameter and 3 floors. And the facility will be providing all of the basic needs for the astronauts, but also to operate a proper greenhouse on Mars. So we will have the dormitory, the beds, toilets, a small kitchen, dining room, entertainment, and relaxation area, but also an extensive food production and areas for the reservoirs, research laboratories, which I am considering here the dry and the wet lab, some photobioreactors to cultivate microalgae, also an airlock for an emergency escape route. This is really necessary, especially considering that we have the connection with the other facilities. And the germination area, a seed storage area, an hygienization area, and also a processing room. I am considering here the internal division of the circumference shape module with in the ground floor, we would have the photobioreactors, the laboratories, the hygienization, the storage, the processing, and also an area for monitoring systems and all of the technological stuff. And then in the first floor, we would have the dormitory, kitchen, and toilet with some entertainment areas. And integrating, as you can see in the right picture, considering the circumference shape, then we would integrate that with another model, which this model will be the Mars Boreal greenhouse. So for this approach, I'm considering all of the capabilities that this greenhouse can propose to us and integrated with the current model that we already have. So we will have an extensive area for food production over here, also the reservoirs, and also a backup water reservoir with some aeroponic systems, germination, an area for germination, and many other capabilities that this model can promote to us. Considering the technological solutions, we can consider that the greenhouse growth systems will be directly dependent on the infrastructure. So all of the considerations to put a plant to grow on Mars will be based on the infrastructure that we have available to us. So considering that we have the Mars Boreal greenhouse, we can start proposing different approaches for the technical systems and also the technological systems. The life support systems will be providing energy, water, food, and breathable air. We will have closed loop systems with the coupled reservoirs to avoid widespread contamination. Then we would have optimized biosystems to guarantee proper energetic performance and also an efficient operation. We would use some support technologies. I'm considering here automated and autonomous systems. So an example would be a robotic arm, and this will be supporting the operational procedures, also providing data, detect failures, some capabilities on water reuse, and also recycling practice. And the monitoring systems will be especially for the crop statistics, the water quality, and the detection of disease in the plants, in the water also, and the biosystems status. And to build all of the systems, all of the biosystems, we need to consider an approach of integration of technologies for the farming environment. So we can have all of the possible technological solutions integrated in one area. So we can have vertical farming, hydroponics, aeroponics, aquaponics, control, renewable energy, and all of these, as you can see here, considering also the LED lightings for artificial lighting, AI, machine learning, sensing, automation, algae, as I previously mentioned, and also some biotechnologies such as GMO, biorepositories, phytopurification, and bioremediation. So with all of this, we can build a controlled ecological life support system, integrating all of the capabilities, all of the plants that we have available, and also put astronauts over there, not only to produce food, but especially to provide the oxygen for the astronauts. And I bring here just some examples of soilless cultivation systems. As I mentioned, we can have hydroponics, we can have aeroponics, aquaponics. This is some diagrams of drip systems, also a deep water culture and aquaponic system. These pictures was taken from this paper called Current Status and Future Challenges in Implementing and Upscaling a Vertical Farming System. So currently we have at Habitat Marte the aquaponic systems integrated with a deep water culture, but also with a nutrient film technique. And also in this slide, you can see the other possible technical setups for the biosystems, for the cultivation system. So you can have the NFT, the food and drain. It's also called overflow or ebb and flow system, and also the aeroponics. All of these solutions, as I mentioned, can be integrated, and we can have different systems that coupled between them. And all of these will be guaranteeing us a system, a robust system that can provide food for the most time for a regular time in the station, and also avoid any situations, any possible challenges, implications that may occur that are not predicted for the astronauts. I bring also here some doing an internship. This is it's called pink farms. This is a urban and a vertical farming here in, and as you can see, it's integration of the vertical also with LED lightnings. As you can see, we have the pink color, which is an integration of blue and red wavelengths. And also a systems I can mention to you that we have also some systems monitor that they were able to cultivate some peppers in space. So this is just to let you know, the APH, the Advanced Plant Habitat Chamber, has an amount of 160 sensors, cameras all over around, and it's the most autonomous and automated system that we have until now operating in space. And another example, this is more a conceptual example. This is the Sirona project. The Sirona provides us an approach considering a living area for the astronauts, but also integrated with a greenhouse. So as you can see also in this picture, we have the integration of technologies such as the robotic arms, some vertical gardens, also the aquaponic reservoirs with some fishes. So as I mentioned, this will be, if we want to build a space greenhouse, a greenhouse on Mars, we need to integrate all the possible technologies that will be available for us. Well, some resources to be generated in situ. Considering the cultivation of microalgae, we can have photobioreactors to cultivate this algae. And the algae, the microalgae, is really useful to provide edible biomass, can be also a biofuel. It's possible to make the CO2 to O2 conversion, and also make some effluent treatment. I bring here just an example of an edible biomass made with algae. This is a spirulina bar, not cereal. It's a spirulina bar that was made in the ISS with the algae cultivated over there. So this is really interesting. And just to let you know, a microalgae, especially the spirulina, can provide an amount of 60% of protein into this bar. So this is just a big overview about algae, the integration of green and space technologies. So algae can be used in many different ways, and NASA has showed that in this picture. So some resources also to be generated in situ, we can consider the custom manufacturing, not only with the 3D printers, but also we can have plant-based manufacturing, or also called biomanufacturing. So we can provide bioenergy, generating energy with wastes or organic matter, like using a biodigester. Also, we can have a biopharma using plants as raw materials for medicines, and also provide some phytotherapies and biostructures. And as you can see in this right picture, we can use the bamboo which can be cultivated in the greenhouse, but also the structure was utilized as a system, as a like a tower for a vertical system, cultivation system. So this is very interesting approach, and it's really useful and open our minds to all of the possibilities that we can have on Mars. And also the in situ resource utilization. I bring here the use of the Martian regolith. In the left picture, you can see some earthworms that was used in this research. This is a research conducted by Dr. Wemelink in Netherlands, which has come up with some results on the use of the Martian regolith, analog regolith, to cultivate crops. And on the right picture, just to see the process turning the regolith of the Martian environment and using it for food production, and also use as a biocomposite to build structures, bricks, and others. Some resources to be transported. I'm considering here some modified seeds with like genetic modifications to support the harsh environment of space, and also the space flight, the transit from Earth to Mars. Some pollinating insects such as bees and ladybugs, germplasm banks, and also other living organisms that maybe can be useful for the greenhouse. Considering the organizational structure, I'm proposing here 3 permanent vacancies: the GM, the greenhouse manager, the BT, the biotechnologist, and the AB, the astrobotanist, and 1 rotating position, which I'm calling the visiting assistant. The VA will be filled in rotation in order of drawing among the members of the mission. I will be explaining with more details about the VA in the next slides. But previously, the role of the facility manager can be assumed based on the experience in farming systems. So it can be like if we want to select the manager of the greenhouse, we can select based on the priorities. Such an example, if we are in the initial phase to implement the greenhouse, maybe it will be more interesting to have as a manager an engineer, a people with an engineering background that can provide some insights on the like implementing the systems. But once we start the cultivation of crops and see how plants are behaving in the space environment, would be more interesting to have as a manager a people with a background in botanist. So it can be different. It can be based on the necessities and priorities of activities that will be held in the structure. So the GM will be responsible for carrying out significant activities and meetings with the other members in the other structures, and the position can be switched between them for a specific time. Some backgrounds that I can imagine here would be agronomy, biosystems engineering, biologists, botanists, biotechnologists, and also specialists in bioregenerative life support systems. Some attributions of the profiles and some duties. The GM will be responsible for decision making, analyze environmental data and reports, and conduct in situ activities. The AB will monitor the adaptive behavior of plants, plan and also establish the dynamic of cultivation and harvesting events. And the BT will be responsible for biosystem management, coordinate the experiments and activities in both laboratories, especially on the dry laboratory. And also will be responsible for the installation and maintenance of equipment associated with plants and algae. And also regarding the VA, it can be filled by the other crew members. Considering the logistic approach that I've mentioned in the beginning of this presentation, we can have different backgrounds near of the greenhouse. So we can have like a doctor, a people with a medical background, a geologist, astrobiologist. So considering that we have different backgrounds in the crew, it's very interesting to have one of them rotating, like select one astronaut to be there in the greenhouse to know more about the systems, to know more about the greenhouse, how all of the things operate. And especially if we are considering that each one of the facilities will have a food microproduction model. So with that, it's very interesting for all of the crew have a minimal knowledge and also to know how to operate, to manage, and also to conduct some maintenance with the cultivation systems. It's possible to provide, it will be possible to provide a mutual exchange, aiming not only the interaction between the astronauts, which will contribute to the mental health of the crew, but also to encourage co-creation practice among the astronauts. So such an example, if we have people with a medical background and it's possible to develop a new medicine using a specific crop. So this is a very interesting thing because that doctor, that astronaut with that background in medicine can go to the greenhouse and start cultivating that specific phytotherapeutic specific crop and really start building that medicine and with the whole crew. So this will be very interesting to provide new innovations, new solutions in the Martian habitat. And also this will be providing, this will be making possible to carry out some experiment, aiming not only at the greenhouse or other structures, but specifically conducting some research related to living systems. Considering some basic features to be incorporated in the astronaut training program, this is more an overview that I'm considering here, because I believe that all of the astronauts need to have this minimal knowledge about all of these features. So considering the sustainable human presence in space, have knowledge in maintenance, and also how to provide a sustainable habitat operation, how to support long-term effects of isolation, also to have some capabilities to handle the architectures and also the technologies for human exploration, practice to reduce costs and technical risks in overall systems, and also conduct some meetings for crew decision making and have new skills based on situations identified on Mars, at Mars. This will be integrated also with simulations. Just to explain you these last two topics, it's very interesting because if we consider that what we currently know about Mars is based on the rovers or orbiters that was sent to there, and also some experience that was provided from the lunar mission and also at the ISS. So the astronauts, once they arrive on Mars, they will be really facing the real situation on Mars. So it's really necessary to be prepared for possible situations that was not predicted. Some videos that I'm suggesting here, how what you eat affects your brain. This is very interesting for all of us to know. Like if I eat a carrot, for example, I know that this carrot can be good for my vision. So this is a brief example. So if we know that, we can use in our benefit. Also, there are other videos, 3D printed fake meat. This is just showing you current technologies to print meat, some veggie meat. Also, another two videos is, the first one is using the spirulina as a fish food. So if we consider an aquaponic system, it can be really interesting. Use that to feed the fish. to feed the fish, and also using spirulina to produce oxygen and food in space. This is actually a video at ISS just explaining the photobioreactor and the production of spirulina at ISS. Considering the resources, I bring here to you just a brief overview about the metabolic inputs and outputs for a crew member, considering an ecosystem, the environmental control life support system. So considering one human, we can have the water, the food, the potable water, the drinkable water, and the oxygen consumption, and the other gases, liquids, solids that are provided by each one of the members. And considering the resource necessary for 2 weeks, as I mentioned, we have the Mars Garden, the Mars Boreal module. So all of this information that we'll be providing to you in this slide and the next one was provided in the paper, Mars Garden, an engineered greenhouse for sustainable residence on Mars. So with that structure that I have showed you, we can consider that the astronauts will be consuming an amount of 0.84 kilograms of oxygen a day, and also will be producing 1 kilogram of CO2 per terrestrial day. The plants will be producing 4.1 kilograms of oxygen a day and consuming 5.6 kilograms of CO2 a day for photosynthesis. And these calculations on the estimated production of the gases by astronauts and crops shows us that it's capable to produce 100% of the oxygen needed by the crew, and the astronauts can supply up to 70% of the CO2 providing that to the plants. So this just to have an idea about what we are producing and what we are consuming, and this 30% will be provided by the other systems, and even for like taken from the external environment and making some conversions with MOXIE and others. Just a big overview about that. And considering on biomass, system consumption, and environment, this will be the Mars Boreal greenhouse has capability to produce kilograms of some calories, some numbers for calories, carbohydrates, protein, and oils, just so you know. The system consumption, we can consider 125 liters of water and an average, I would say 40 kilowatts of like in a normal situation, like considering a peak demand, like when we have all of the systems, all of the crops are growing well, and all of the LED lighting systems in the like providing the most light intensity as possible. So we can consider this peak of 53.5 kilowatts. Some data on the environment: the temperature will be between 33 and 23 and 26 degrees Celsius. The pressure will be an amount of this number, and the CO2 levels, as you can see, also in some ppm. So considering the food that will be consumed by the astronauts and also the potable water, we can consider that the diet and amount of food that will be consumed by each astronaut will be specific to each individual. So it may diverge if considering the weight, the height of the astronaut, the biotype, and the routine. So different routines, different biotypes, this will be directly affecting how much the astronauts will be eating. So I'm considering here an average of daily consumption of 2.1 kilograms by person. And just to let you know, I'm I do not bring this number like for like by nowhere. I have bring this as a result from this paper called Greenhouse Production Analysis of Early Mission Scenarios for Moon and Mars Habitats. This was a research conducted at Eden ISS, and they has um, they had analyzed the best approach of cultivation, harvesting events, and also the storage status. So considering this number, this specific number of 2.1 kilograms, we would have, this would be meeting the daily demand of astronauts, the biomass consumption, but also will be increasing the biomass storage status. So this will be a balance between both of the storage and the consumption. Making the calculations here for a week consumption, and then for the 3 astronauts, we would have for 2 weeks an amount of food with 205.8 kilograms of food. And the water, if we consider that the astronauts will be drinking 3 liters of water per day, we would have in 2 weeks an amount of 126 liters of water. This is very interesting to tell you that this number of water consumption is based on what will be the best for us here on Earth. So on Mars, this will maybe will be different, like more or less depending on the guidelines to other facilities. All of this, it's possible to develop protocols and routines to be applied on the food microproduction system in each facility. So with some guidelines that will be I'm providing here in this presentation for you, for all of you. It can be useful to be presented as the guidelines for food microproduction systems in your facilities. Also, some regular research and development of technologies to improve crop growth and food processing, also provide indicators for food logistics, such as food consumption, control of irrigation water, and also storage status. And provide also some base guidelines and training for handling and preventive maintenance of biosystems to be added in to the astronauts' routines. So as I mentioned, it's very interesting to have all of the astronauts having a minimal knowledge in the biosystems in the operation of the greenhouse and also the microproduction module. Some protocols and routines, considering now we would have monitoring routines, also conduct tests allowing that specifically, and also will be possible to perform preventive maintenance of the biosystems and preserve the good condition of the cultivation beds, collect reports from the other stations, and compare with data reported by sensors, and develop some activities in analysis, diagnosis, also ensure the circularity of the systems and detect some possible failures, and specifically providing orientations for astronaut training. I bring here also just so you know some routines that was considered in a paper. I'm not remembering exactly the name of the paper, but this was a paper written by Dr. Lucy Pollitt, which is a PhD at NASA, and she has made a research in the ISS specifically on veggie, and also has compared with some data on analog stations around the world, considering the time and the tasks associated to food cultivation. So she has pointed all of the tasks, activities associated with food cultivation, and I bring here just to and have a big overview about all of the activities, all of the routines that are related with. So I bring here the health monitoring activities, not only on the environment, but also the crops to see disease, pathogens, and check up temperature, relative humidity, and the other parameters. The cultivation operations, all of these operations, as you can see, harvest processing, and also some routines operation and the maintenance. And I bring also these two different ones. The orange, the highlight, the two operations highlighted with orange, the plant data collection and the system data collection, would be very interesting with if we have the monitoring systems, the technology operating together with the astronauts. This will be especially useful to reduce the workload of the astronauts. I can mention others also, but this is the most like useful one, because it will be possible to provide some reports, to analyze data, provide graphics, and many others. And also highlighted in blue, we can have the leisure time. So it's really important to consider our greenhouse as an area also to relax and have a sensory experience with plants. Okay, and also I bring here some current protocols on food cultivation that we have implemented, me and Professor Julio and other astronauts that has participated in previous missions. We were able to develop all of these protocols associated with the Habitat Marte greenhouse, the biohabitat. So we have the protocols to food cultivation, for food system maintenance, to build space food systems, build greenhouses, not only the structures, but also the environmental control, protocols for food harvesting, food processing, for evaluation of contamination and plagues, and also to process food waste on harvesting and also on cooking. I bring here also some routines that we have developed there on the biohabitat greenhouse. As you can see, we have the three main type of routines: the management, the maintenance, harvesting, processing. And but I will be just covering for now some of the pictures, just to let you know. This left top one, we were cleaning the fish tank at the biohabitat greenhouse. This is a maintenance activity. Then we have the harvesting event. Also, we were harvesting the fish, conducting some analysis on water quality. The water, like to see how is the components, the chemical components of the water, and the amount of each one of these components. Also to analyze the plant health and also the fish health. So I have highlighted here all of the routines. This has increased. This was especially for 2020, and until now, I'm sure that I'm not current at Habitat Marte participating in person in the missions, but I'm sure that these activities has increased. We have many other activities associated to all of these topics and also other topics. Considering the protocols of safety, I bring here some ideas for fast isolation, like in case of isolation, each facility would be analyzing the available resources, evacuation, to guide the other members regarding the system maintenance, or even like emergency situation, to make a rationing order if necessary, and the optimization of food distribution, if necessary, starting the rationing order to start the resource containment and food rationing procedures. Also, some protocols related to keep the reliability of the system. So monitor and tabulate the response of the systems to emergency situations, and perform the inventory of losses and the recovery schedule. Then we would have the self-awareness, like to identify and analyze the critical points of the structure with the respective response to emergency situations and tabulate the data. And for the protocols of safety, I consider here this indicator, which is called risk priority number, the RPN. The RPN is an equation of these scales, like the severity scale of the risk, the occurrence scale, and the detection scale. And just to provide you here some ideas on what we can consider as a risk or not. So the severity scale, we can vary from the catastrophic to minimal severity, the occurrence to high and low occurrence, and the detection like almost impossible and almost certain. So based on each situation that could be identified, this is some scales that we would have to really indicate the priority of the risk. What risks we need to concentrate to solve them as much fast as possible. Some types of failures, we can have some failures on hardware maintenance, hardware and human error, software maintenance, software and human error, and hardware and software and others. So as you can see here, we have the definitions for each one of them, just to like highlight what are the possible situations of failures that maybe will be identified in future situations on Mars. And also, this is a risk assessment spreadsheet, considering each one of the systems, the risks associated, and what are the possible mitigations. And also we can have the consequence, the likelihood consequence, and the mitigation. So this is very interesting. It's very necessary to all of the astronauts has idea of each one of these risks associated to the cultivation systems. In case of any situation, it's necessary. It would be interesting to provide a kind of a report talking about this, what system is not functioning well, what are the risks involved, how will be mitigated when it has happened, and having all of the data associated to that risk to have like are responsible for the maintenance of the systems, have idea of what are the procedures, the guidelines to be conducted, like to avoid this risk or overcome the situation. And this is just the continuation of this spreadsheet. Protocols for occupancy. So as I mentioned, we are dealing with humans, so it will be necessary to have socialization practices with alternative routines. I'm always considering the cooking classes because based on some missions that I have participated at Habitat Marte, considering that we have harvested the tilapia fish, I was really motivated to start knowing to make sushi, to cook some fishes and having some fun during this harvesting, during these cooking events. This is very interesting, like to diversify on the activities, on the routines. There are some recreational moments in relaxing areas. Also, the planning of the plantations will have contributions from the entire team, so they can expose their preference of food. So considering that, okay, I am from Brazil, I like that type of sauce in my food, and maybe an astronaut from India like different crops, different type of sauce for their food. So this is very interesting to provide the opportunity to cultivate different type of crops to allow the astronauts to be more near of their culture. So just an example on that. Also, I'm considering the human-plant interaction. So the operational activities on the structure involving the cultivation of food and interaction with plant. So this is very interesting. And will be interesting to schedule the use of the greenhouse as a social space. This is also necessary to have a well-defined protocol considering hygiene and other important procedures associated with the food cultivation to avoid contaminations. Here's some pictures at ISS, National Plane Chest, also a dinner moment. So this is always also possible things that will be happening in the routine of the astronauts. And also considering food production with 3D printers. I do not bring here any protocol for that, but just to have an idea about what are the possibilities, what can do with the 3D printers. The basic needs to print something, it will be necessary the material, the raw material. If we are considering food, we will have a biomaterial to build that, and we would design the shape of what we want to operate. Provide some diversity, some nutritional stability on the food, provide attractive food with more acceptability. As you can see in the left picture, we have some a pancake in a national shape. So this is very interesting and looks like delicious also. And also, as I mentioned previously mentioned, the 3D printed meat. So this is vegan meat, and it can be also complement the diet that was cultivated in the greenhouse. And now talking about the spin-offs, bringing here some solutions to be applied on Earth. All of these that I have presented here to provide technologies for efficient crop water usage and also energy. Provide also enclosure structures for efficient resource saving and environmental control. Biosystem modeling to guarantee reliable and redundant operation on food cultivation. Delivers with lowest possible handling and corrective measures. Implementation of closed loop systems to guarantee adequate amount of nutrients for the plants. And also avoid some water waste. And some autonomous managed food systems to reduce extensive workload on traditional agriculture. So we are in a transition, almost in the end of this transition. It's more familiar to us that we are, the agri-tech sector is emerging. We have many technologies associated with agriculture for now, and they are becoming even more viable to all of us. And space studies, space agriculture is here to increase all of this familiarity and making this technology even more accessible. Some guidelines should be applied on Earth. The efficient crop water usage to sustain life, develop new abilities to grow food, establish parameters for easy assembly and maintenance, and solutions to keep the confidence related to plant growth. This is actually an example of the biohabitat greenhouse. The biohabitat greenhouse has provided, at Habitat Marte, has provided us a lot of capabilities, knowledge, and experience related to food cultivation. More than 2 years of experience with this research, not only provide guidelines to us, and for me also to be here talking with you about space greenhouses, but also providing guidelines that will be useful to support people in vulnerable situations, vulnerable communities, as such as the case of the location of Habitat Marte, which is a place which is located in a place, semi-arid region, which face a lot of droughts, high temperatures, and like a really harsh environment, extreme environment here on Earth. And the impacts on SDGs, how does the operation of the infrastructure results and of the infrastructure and results impacts on sustainable development goals. So I bring here in previous mission was provided a big overview with all of 17 sustainable development goals that a previous member has made some connections with all of the sustainable development goals. So the greenhouse can be connected with all of these. But I bring here the most important ones in my point of view, which is avoid hunger, should be, make zero hunger, provide a good health, build sustainable cities and communities, and really make a responsible consumption. And for me, the most important one, support on climate action to overcome the situations on climate change and avoid even more the degradation of the natural resources. So we are here to provide us, we that are in the space sector, we know that space is here to contribute with that, and we need to widespread that to everyone. Everyone needs to know, and if not us that provide this knowledge for people, who will be doing that? Who will be doing that? So it's our responsibility to share and show that space is here to contribute, especially on climate action, to overcome these bad situations that are occurring with our ecosystems and in a big overview with our planet. So I bring here, just so you know, we are now open to a new horizon of technological deliverables that can support sustainability while reducing negative impacts of climate change. Space exploration not only generates knowledge for human living off Earth, but also help us to find solutions to societal problems and inspires people to act for a more humanized and sustainable society. So these are my references. Thank you very much for your attention. It was a big pleasure to be here with you. For those who will be watching this presentation in the YouTube channel of Habitat Marte, feel free to contact me on email, Instagram, and LinkedIn. I'm totally open for questions for the crew and for those who want to make questions in future moments. Thank you very much.